This presentation is delivered by the Stanford Center for Professional Development.
So, welcome back. And what I want to do today is continue our discussion on support vector machines. In particular, I want to talk about the optimal margin classifier. Then we'll take a brief digression to talk about primal and dual optimization problems, and in particular, what's called the KKT conditions. And then we'll derive the dual to the optimization problem that I had posed earlier. And that will lead us into a discussion of kernels, which I won't really, which we'll just get to say a couple of words about, but which I'll do properly only in the next lecture. And as part of today's lecture, I'll spend some time talking about optimization problems. And you know, in the little time I have today, I won't really be able to do this topic justice. I won't be able to talk about convex optimization and do that topic justice. And so at this week's discussion section, the TAs will have more time. We'll teach a discussion section focused on convex optimization. Okay, so it's a very beautiful and useful theory. So you want to learn more about that, listen to this Friday's discussion section. Just to recap what we did in the previous lecture, right? As we were beginning our development of support vector machines, I said that our hypothesis will be represented as H subscript WB as G of W transpose X plus B, where G will be plus 1 or minus 1, depending on whether Z is greater than or equal to 0. And I said that in our development of support vector machines, we'll change the convention of letting Y be plus 1, minus 1 to denote the cross labels. So last time, right, we also talked about the functional margin, which was this thing, gamma hat I. Right. And so we had the intuition that if the functional margin is a large positive number, then that means that we are classifying, training example correctly and very confidently, right? So if yi is plus 1, we would like W transpose xi plus b to be very large, and if yi is minus 1, then we'd like W transpose xi plus b to be a large negative number. So we sort of like functional margins be large. But I also said functional margin has a strange property that you can increase functional margin just by, say, taking your parameters W and B and multiplying them by 2. And then we also defined the geometric margin, which was that which is essentially the functional margin divided by the norm of W. And so the geometric margin had the interpretation as being, you have a few training examples. The geometric margin of the example is sort of has the interpretation as the distance between the training example and the hyperplane. Right? And it will actually be a signed distance, so that this distance will be positive if you're classifying the example correctly, and if you're misclassifying the example, this distance will be sort of the minus of the distance between the training example and your separating hyperplane, where the separating hyperplane is defined by the equation W transpose X plus B equals 0, right? Okay. So, and I guess I also defined these things as the functional margin and geometric margins with respect to a training set I define as the worst case, or the minimum functional geometric margin. So in our development of the optimal margin classifier, our learning algorithm would choose parameters W and B so as to maximize the geometric margin. So our goal is to find a separating hyperplane that separates the positive and negative examples with as large a distance as possible between the hyperplane and the positive and negative examples. And if you go to choose parameters W and B to maximize this, just to point out one property of the geometric margin is that you can actually scale W and B arbitrarily, right? So if you look at this definition for the geometric margin, I can choose to multiply my parameters W and B by 2 or by 10 or by any other constant, and it doesn't change my geometric margin, right? And one way of interpreting that is you look at this separating hyperplane. You look at this line, separating my positive and negative training examples. If I scale W and B, that doesn't change the position of this plane, right? Because the equation WX plus B equals 0 is the same as the equation 2W transpose X plus 2B equals 0. So it gives the same straight line. And what that means is that I can actually choose whatever scaling for W and B is convenient for me. And in particular, we'll use this in a minute. I can impose a constraint like that the norm of W must be equal to 1. Right? Because this means that you can find a solution to W and B, and then by rescaling the parameters, you can easily meet this condition. Just rescale W to the norm 1. And so I can add a condition like this and essentially not change the problem. Or I can add other conditions. I can actually add a condition that, the absolute value of W1 be equal to 1. I can add only one of these conditions, right? Not both of them. We can add a condition that the absolute value of the first component of W must be equal to 1. And again, you can find the optimal solution and just rescale W and B to meet this condition. And I can add other more esoteric conditions like that, right? Because again, this is a condition that you can solve for the optimal margin, and then just by scaling, W up and down, you can ensure you meet this condition as well. Okay, so again, I can only choose one of these conditions, right? Not all of them. And so our ability to choose any scaling condition on W that's convenient to us will be useful again in a second. All right. So let's go ahead and write down an optimization problem. And again, my goal is to choose parameters W and B so as to maximize the geometric margin. Here's my first attempt at writing down an optimization problem. I actually wrote this one down right at the end of the previous lecture. Going to solve for parameters gamma W and B such that that holds, for all M training examples. And let's say I choose to add this normalization condition. Okay. So if the norm condition that the norm of W is equal to 1, this makes the geometric and the functional margin the same. And so I'm saying I want to find a value for gamma that's as big as possible, so that all of my training examples have functional margin greater than or equal to gamma. And with the constraint that norm of W equals 1, functional margin and geometric margin are the same, right? So this is saying, find a value for gamma so that all the values, all the geometric margins are greater than or equal to gamma. Okay. So if you solve this optimization problem, then you have derived the optimal margin classifier. But this is not a very nice optimization problem, right? Because this is a nasty non-convex constraint. In particular, it's asking that you solve for parameters W that lie on the surface of a unit sphere. Has norm 1s. It lies on a unit circle, a unit sphere, right? And so if we can come up with a convex optimization problem, then we'd be guaranteed that algorithms like gradient descent or other local search algorithms would not have local optima. And it turns out this is an example of a non-convex constraint. So this is a nasty constraint that I would like to get rid of. So let's change the optimization problem one more time. Now let me pose a slightly different optimization problem. Let me maximize the functional margin divided by the norm of W, subject to yi W transpose xi. Okay. So in other words, I want to find a number gamma hat so that every one of my training examples has functional margin greater than or equal to gamma hat. And my optimization objective is I want to maximize gamma hat divided by the norm of W. Okay, so I want to maximize the functional margin divided by the norm of W. And you know, we saw previously, right? The functional margin divided by the norm of W is just a geometric margin. So this is a different way of posing the same optimization problem. So I'm seeing some slightly confused looks. Are there questions about this?
The second statement that has to be greater than the functional margin.
Right.
Why are you dividing it by? Why did you just have it the geometric margin? Why do you? Is there some trick there that's important or not?
Oh, wait, say that again?
So the second statement, we're saying greater than the functional margin. You're not dividing by the norm of W.
Oh, I see. Yes.
Is that important?
Let's see. So this is the functional margin, right? This is not the geometric margin.
Yeah.
So, I want to divide by the norm of W my optimization objective.
I'm just wondering how come you're not dividing also in the second statement? Once you're greater than the functional margin, why are you dividing there by the norm of W?
Let's see. Not sure I get the question. Let me try to explain this again. So here's my goal. I want an optimization. So let's see. The parameters of this optimization problem are gamma hat W and B, right? So I'm going to have like a convex optimization software solve this problem for some set of parameters gamma hat W and B, and I'm imposing the constraint that whatever values it comes out with, you know, yi times W transpose xi plus B must be greater than or equal to gamma hat. And so this means that the functional margin of every example had better be greater than or equal to gamma hat. Okay? So there's a constraint that the functional margin is greater than or equal to gamma hat. But what I care about is not really maximizing the functional margin. What I really care about, in other words, in my optimization objective, is maximizing gamma hat divided by the norm of W, which is the geometric margin. Okay? So in other words, my optimization problem is I want to maximize the functional margin divided by the norm of W, you know, subject to that every example must have, you know, functional margin at least gamma hat. Does that make sense now?
When you say that you maximize gamma or gamma hat with respect to gamma W and B, or with respect to gamma hat W and B, does it mean that in this case gamma and gamma hat are no longer a function of W?
Yeah, right. Okay, so this is the right. So it turns out, so this is how I write down an optimization problem in order to solve for the geometric margin. What is it? So it turns out that the question is gamma hat a function of W and B? And it turns out that in my previous mathematical definition it was, but the way I'm going to pose this as an optimization problem is I'm going to ask the convex optimization solver. Say, let's say I have software. Let's say I have software for solving convex optimization problems, right? Then I'm going to pretend that these are independent variables and ask my convex optimization software to find me values for gamma, W, and B to make this value as big as possible and subject to this constraint. And it'll turn out that when it does that, it will choose, well, it'll obviously choose gamma to be as big as possible, right? Because the optimization objective is you're trying to maximize gamma hat. So for a fixed value of W and B, my software would choose to make gamma hat as big as possible. Well, but how big can it make gamma hat? Well, is limited by these constraints, right? It says that every training example must have functional margin greater than or equal to gamma hat. And so the biggest we can make gamma hat will be the value of the smallest functional margin. And so when you solve this optimization problem, the value of gamma hat you get out will be indeed the minimum of the functional margins of your training set. Okay, so Justin?
Yeah, I was just wondering. I guess I'm a little confused because it's like, okay, you have like two clouds of data, and you could say, okay, please draw me a line such that you maximize the distance between the smallest distance from between that line and one of the data points. And it seems like that's kind of what we're doing, but it seems like this is more complicated than that. And I guess I'm wondering what is the difference.
I see. So I mean, this is the question is of right, two clouds of data, trying to find serving hyperplane, and this seems more complicated than trying to find the line that separates the clouds data. So I'm just repeating questions in case, since I'm not sure how well the audio captures it. So the answer is, this is actually exactly that problem. This is exactly the problem of, given two clouds of data, positive and negative examples, this is exactly the formalization of the problem where our goal is to find a line that separates the positive and negative examples, maximizing the worst case distance between any point and this line. Okay, yeah, Tim?
So why do you care about the worst case distance?
For now, why do we care about the worst case distance, right? For now, let's just care about the worst case distance for now. We'll come back and we'll fix that later. Caring about the worst case distance is just is a nice way to formulate this optimization problem. I'll come back and actually change that later. Can you raise your hand if this makes sense? If this formulation makes sense? Yeah. Okay. Cool. Great. So let's see. So this is a different way of posing the same optimization problem. And on the one hand, I've gotten rid of this nasty non-convex constraint. But on the other hand, I've now added a nasty non-convex objective. In particular, this is not a convex function in parameters w, and so you don't have the usual guarantees. Like if you apply gradient descent, this will converge to global minimum. Okay? At least that does not follow immediately from this because this is non-convex. So what I'm going to do is, earlier I said that I can impose any of, a number of even fairly bizarre scaling constraints on W, right? So I can choose any scaling constraint like this and things are still fine. And so here's the scaling I'm going to choose to add. Again, I'm going to assume, for the purpose of today's lecture, I'm going to assume that the examples are linearly separable, that you can actually separate the positive and negative classes, and we'll come back and fix this later as well. But here's the scaling constraint I want to impose on W. I want to impose a constraint that the functional margin is equal to 1. Okay? And another way of writing that is that I want to impose a constraint that min over I, yi, that, okay? That the worst case functional margin is equal to 1. And clearly, this is a scaling constraint, right? Because if you solve for W and B, and you find that your worst case function margin is actually 10 or whatever, then by dividing through W and B by a factor of 10, I can get my functional margin to be equal to 1. Okay? So this is a scaling constraint I'm going to imply, and this is more compactly written as follows. This is imposing a constraint that the functional margin be equal to 1. And so if we just take what I wrote down as number 2, our previous optimization problem, and add this scaling constraint, we then get the following optimization problem. Min over W and B. Okay. I guess previously we had a maximization over gamma hat divided by the norm of W. So let's maximize 1 over the norm of W. But so that's the same thing as minimizing the norm of W squared, right? Max 1 over norm of W is the same as min W, norm of W squared. And then these are our constraints. Since I've added the constraint to the function margin was equal to 1. Okay. And this is actually my final formulation of the optimal margin classifier problem, at least for now. Okay. So the picture to keep in mind for this, I guess, is that our optimization objective is we want to minimize the norm of W, and so our optimization objective is just a big quadratic function, right? And there's B somewhere in this picture to be control it. So, your parameters W1 and W2, and you want to minimize a quadratic function like this. So, a quadratic function just has contours that look like this. And moreover, you have a number of linear constraints in your parameters. So, you may have a linear constraint that eliminates that half space, a linear constraint that eliminates that half space, eliminates that half space, and so on. And so the picture is you have a quadratic function and you're ruling out various half spaces with each of these linear constraints. And I hope if you can picture this in 3D, I guess a controller in 3D, I hope you can convince yourself that this is a convex problem that has no local optima. Right? That if you run gradient descent within this set of points that hasn't been ruled out, then you converge to the global optimum. And so that's a convex optimization problem. That's sort of nice and relatively easy to solve. Okay. Questions about this? Okay. Actually, just raise your hand if this makes sense. Okay, cool. So this gives you the optimal margin classifier algorithm. And it turns out that this is a convex optimization problem. So you can actually take this formulation of the problem and throw it at off-the-shelf software, what's called a QP, or quadratic program solver. This sort of optimization problem is called a quadratic program, with a quadratic convex objective function and set of linear constraints. So you can actually download software to solve these optimization problems for you. Usually, I actually wouldn't use gradient descent because you have constraints like these, although you could actually modify gradient descent to work for this too. So we could just declare success and say that we're done with this formulation of the problem. But what I'm going to do now is take a digression to talk about primal and dual optimization problems. And in particular, I'm going to later I'm going to come back and derive yet another very different form of this optimization problem. And the reason we'll do that is because it turns out this optimization problem has certain properties that make it amenable to very efficient algorithms. And moreover, I'll be deriving what's called the dual formulation of this that allows us to apply the optimal margin classifier even in sort of very high dimensional feature spaces, even in sometimes infinite dimensional feature spaces. So we can come back to that later, but let me now spend some time talking about convex optimization. So I'm actually curious, how many of you, from like, I don't know, calculus, remember the method of Lagrange multipliers for solving an optimization problem, like minimum or minimization or maximization problem subject to some constraint? How many of you remember like the method of Lagrange multipliers for that? Oh, okay, cool. Some of you, yeah. So if you don't remember, don't worry. I'll describe that briefly here as well. But what I'm really going to do is talk about a generalization of this method of Lagrange multipliers that you may or may not have seen in like some calculus classes. But if you haven't seen it before, don't worry about it. So, the method of Lagrange multipliers was, well, suppose there's some function you want to minimize. You want to minimize f of w, but subject to some set of constraints that hi of w must be equal to 0 for all I equals 1 through L. Okay, and given this constraint, I'll actually usually write it in a vectorial form, in which I write h of w as this vector valued function. Gonna say that is equal to 0. Okay, where 0 with the arrow on top, I use that to denote the vector of all zeros. So you want to solve this optimization problem, right? Some of you have seen the method of Lagrange multipliers where you construct what's called a Lagrangian. right? Which is your original optimization objective plus sum of I Lagrange multipliers times constraints. And these parameters beta I we call the Lagrange multipliers. And so the way you actually solve your optimization problem is you take the partial derivative of this with respect to your original parameters and set that to 0. Take the partial derivative with respect to your Lagrange multipliers beta and set that to 0. And then, you know, this famous theorem proved by, I guess, Joseph Louis Lagrange was that for some value W star to be a solution, it is necessary that there exists beta star, right? The backwards E is there exists. So there exists beta star such that oops, excuse me. Okay, such that those partial derivatives are equal to 0, right? So the method Lagrange multipliers is to solve this problem. You construct the Lagrangian, take the derivatives with respect to the original parameters beta, the original parameters W, and with respect to Lagrange multipliers beta. Set the partial derivatives equal to 0 and solve, you know, for all solutions, and then you check each of the solutions to see if it is indeed a minimum, right? So what I'm going to do is actually write down the generalization of this. Okay, and again, if you haven't seen that before, don't worry about it. This is fine. Right? So what I'm going to do is actually write down a generalization of this to solve a slightly more difficult type of constraint optimization problem, which is, suppose you want to minimize f of w, subject to the constraint that gi of w, excuse me, is less than or equal to 0, and that hi of w is equal to 0. Okay, and again, using my vector notation, I'll write this as g of w is equal to 0, and h of w is equal to 0. So unlike the previous case, we now have inequality constraints as well as equality constraints. I then have a Lagrangian, or is actually sometimes called this a generalized Lagrangian, which is now a function of my original optimization parameters w, as well as two sets of Lagrange multipliers alpha and beta. And so this will be f of w plus okay. Now, here's a cool part. I'm going to define theta subscript p of w to be equal to max over alpha beta, subject to the constraints that the alphas are greater than or equal to 0 of the Lagrangian. Okay. And so I want you to consider, you know, the optimization problem min over w of max over alpha beta such that the alphas are greater than 0 of the Lagrangian. And that's just equal to min over w theta p of w. Okay. And just to give this a name, the subscript P here stands for primal problem, and that refers to this entire thing. This optimization problem that I've written down is called the primal problem. This means this is the original optimization problem we're interested in solving. And later on, I'll derive another version of this, but that's what P stands for. Essentially, this is a primal problem. Now, I want you to consider theta of P, and in particular, I want to consider the problem of what happens if you minimize W, minimize as a function of W, this quantity theta of P. Right. So, let's look at what theta P of W is, right? Notice that if GI of W is greater than 0, so let's pick some value of W, and let's ask what is theta P of W, okay? So if W violates one of your primal problem's constraints, then theta P of W will be infinity, right? Why is that? So coming back to this previous board for a second, suppose I pick a value of W that violates one of these constraints. So GI of W is positive. Then, well, theta P, right, is maximized as a function of alpha and beta, the Lagrangian. So if one of these GI of W's is positive, then by setting the corresponding alpha I to plus infinity, I can make this arbitrarily large. And so if W violates one of my primal problem's constraints, one of the GIs, then max over alpha of this Lagrangian will be plus infinity. Okay. And similarly, and in the same way, because in a similar way, if HI of W is not equal to 0, then theta P of W will also be infinity for a very similar reason, because if HI of W is not equal to 0 for some value of I, then in my Lagrangian I had a beta I times HI term, right? And so by setting beta I to be plus infinity or minus infinity, depending on the sign of HI, I can make this plus infinity as well. And otherwise, theta P of W is just equal to F of W, right? Turns out if I have a value of W that satisfies all of the GI and the HI constraints, then when you maximize in terms of alpha and beta, all of the Lagrange multiplier terms will actually be, the maximum will actually be obtained by setting all the Lagrange multiplier terms to be 0. And so theta P just left with F of W. Thus, theta P of W is equal to F of W if constraints are satisfied, if the GI and HI constraints, and is equal to plus infinity otherwise. Okay? So, the problem I wrote down of minimize as a function of W, theta P of W, this is just the original problem. Right, that's just exactly the same problem as my original primal problem. Because if you choose a value of W that violates the constraints, you get infinity. And if you satisfy the constraints, you get F of W. So this is really just the same as, well, saying satisfy the constraints and minimize F of W. Right? That's really what minimizing theta P of W is. Okay. Raise your hand if this makes sense. Yeah. Okay. Cool. So. All right. I hope no one's getting mad at me for doing so much work and we come back to exactly the same thing we started with. So here's the cool part. Let me now define the dual problem. define theta d, and d stands for dual, and this is now a function of alpha and beta. It's not a function of the Lagrange multiplier. It's not of w. Define this to be minimized over w of my generalized Lagrangian. Okay, and my dual problem is this. Or in other words, this is max over that. Okay, and so so this is my dual optimization problem to maximize over alpha and beta theta d of alpha and beta. Right. So this optimization problem, I guess, is my dual problem. I want you to compare this to our previous primal optimization problem. Right. The only difference is that you know, I took the max and min and I switched the order around to the max and min. That's the difference in the primal and the dual optimization problem. And it turns out that is a fact. Is true generally that d star is less than equal to p star. In other words, I think I defined p star previously. P star was the value of the prime optimization problem. And in other words, that it's just generally true that the max of the min of something is less than or equal to the min of the max of something. This is a general fact. And just as a concrete example, the max over y in the set 0, 1 times, of the min of the set in 0, 1 of indicator x equals y. Right, this is less than or equal to min okay. So this inequality actually holds true for any function you might plug in here, and this is one specific example where the min of xy, min of x of indicate x equals y, this is always equal to 0, right? Because whatever y is, I can choose x to be something different, so this is always 0. Whereas if I exchange the order of the min and max, then this thing here is always equal to 1. Okay, so 0 is less than 1. And more generally, this min max less than the this max min less than the min max holds true for any function you might put in there. But it turns out that sometimes under certain conditions, these two optimization problems have the same value. Sometimes under certain conditions, the primal and the dual problems have the same value. And so you might be able to solve the dual problem rather than the primal problem. Okay? And the reason to do that is that sometimes, which we'll see in the optimal margin classifier problem, the support vector machine problem, the dual problem turns out to be much easier to solve and has many useful properties that we'll make use of compared to the primal. So let's see. For the sake of so what I'm going to do now is write down formally the set of conditions under which that's true, where the prime and the dual problems are equivalent. And so our strategy for deriving a support vector machine algorithm will be that we'll write down the primal optimization problem, which we did previously in the master margin classifier. And then we'll derive the dual optimization problem for that. And then we'll solve the dual problem. And by modifying that a little bit, that's how we'll derive a support vector machine. Right? But let me actually, for now, let me just first, for the sake of completeness, I'll just write down the conditions under which the primal and the dual optimization problems give you the same solution. So So let F be convex. If you're not sure what convex means, for the purposes of this class, you can take it to mean that the Hessian H is positive semi-definite, right? So it just means it's a bow-shaped function like that, right? And once you learn more about convex optimization, again, please come to this week's discussion section taught by the TAs. Let's suppose the HI constraints are affine, and what that means is that HI of W equals alpha I transpose W plus BI. Okay. This essentially means the same thing as linear. Without the term B here, we say HI is linear. When we have a constant intercept term as well, this is technically called affine rather than linear. And let's suppose the GIs are strictly feasible. And what that means is that there exists a value of the W such that for all I, GI of W is less than 0. Okay? Don't worry too much about I'm writing these things down for the sake of completeness, but don't worry too much about the technical details. But strictly feasible just means that there's a value of W such that all of these constraints are satisfied with strict inequality rather than with less than equal to. Under these conditions, there will exist W star, alpha star, beta star, such that W star solves the primal problem, and alpha star and beta star, the Lagrange multipliers, solve the dual problem. And the value of the primal problem will be equal to the value of the dual problem, will be equal to the value of your Lagrange multiplier, will be equal to the value of the generalized Lagrangian evaluated to that W star, alpha star, beta star. In other words, you can solve either the primal or the dual problem, you get the same solution. Further, your parameters will satisfy these conditions. Partial derivative with respect to the parameters would be 0. And actually, if you keep this equation in mind, we'll actually use this in a second when we take the Lagrangian and of our support vector machine problem and take its derivative with respect to W to derive our dual problem. We'll actually perform this step ourselves in a second. Partial derivative with respect to Lagrange multipliers beta is equal to 0. Turns out this will hold true too. This is called the this is called the KKT complementarity condition. KKT stands for Karush-Kuhn-Tucker, which were the authors of this theorem. Well, and by tradition, you usually list 5 KKT conditions, but the other 2 are okay. Just that the alpha i's are greater than 0, which you had previously, and that your constraints are actually satisfied. Okay. So. Let's see, half an hour. All right. So let's take this and apply this to our optimal margin optimization problem that we had previously. I just want to say one word about this, which is, I want to say one word about this KKT complementarity condition. That condition that, sort of at your solution, you must have that alpha star I times gi of w is equal to 0. So let's see. So if a product of two numbers is equal to 0, that means that at least one of these things must be equal to 0, right? For a product of two things to be equal to 0, well, that just the same. Either alpha I or gi is equal to 0, right? So what that implies is that just a Karish-Kuntaker see, most people just say KKT, but I'm going to show you the right spelling of the names. So KKT complementarity condition implies that if alpha I is non-zero, that necessarily implies that gi of w star is equal to 0, right? And usually it turns out, so all the KKT condition guarantees is that at least one of them is 0. It may actually be the case that both alpha and gi are both equal to 0. But in practice, when you solve this optimization problem, you find that to a large part, alpha I star is not equal to 0 if and only if gi of w star is equal to 0. This is not strictly true because it's possible that both of these may be 0. But in practice, when you solve problems like these, for the most part, usually exactly one of these things will be non-zero. And also, when this holds true, when gi of w star is equal to 0, we say that gi of w, I guess, is an active constraint. Because recall, our constraint was that gi of w must be less than or equal to 0. And so if it's equal to 0, then we say that that's a constraint, that this is an active constraint. All right. Once we talk about SVMs, I actually come back and say a couple and just extend this idea a little bit more. Actually, this is on a different board. I might return to this board in a second, but so let's go back and work out what are the primal and the dual optimization problems for our optimal margin classifier, for the optimization problem that we worked out just now. As a point of notation, in what I've been writing down so far in deriving the KKT conditions, my Lagrange multipliers were alpha I and beta I. It turns out when I apply this, to work out the SVM, turns out I only have one set of Lagrange multipliers, alpha I. And also, as I was working out the KKT conditions, I used W to denote the parameters of my primal optimization problem. Right? I want to minimize f of W. In my very first optimization problem, I had an optimization problem with a bunch of parameters W. In my SVM problem, I'm actually going to have two sets of parameters W and B. Okay, so this is just a keep that sort of slight notation change in mind. So, problem we worked out previously was we want to minimize the norm of W squared and just add a half there by convention because it makes some of the math work out nicer. And subject to the constraint that yi times W transpose xi plus B must be really greater than 1. Okay? And so let me just take this constraint and I'll rewrite it as a constraint gi of w comma b. Again, right, previously I had gi of w, but now I have parameters w and b. So I have gi of w comma b defined as this one. Okay. So let's look at the implications of this in terms of the KKT dual complementarity condition again. So we have that alpha I is greater than or equal to 0, right? That necessarily implies gi of w comma b, is equal to 0. In other words, that this is an active constraint. Right? And what does this mean? It means that it actually turns out gi of wb equals 0. That means exactly that the training example xi, yi has functional margin equal to 1, right? Because remember this constraint was that the functional margin of every example has to be greater than or equal to 1, right? And so if this is an active constraint, if this inequality holds with equality, that means that my training example I must have functional margin equal to exactly 1. Right? And so, actually, yeah, right now, I'll do this on a different board, I guess. So in pictures, what that means is that I have some training set, right? There's some separating hyperplane. And so the examples with functional margin equal to 1 will be exactly those which are sort of closest to my separating hyperplane. So that's my equation of W transpose equals V equals 0. And so in this cartoon example that I've drawn, it will be exactly these three examples that have functional margin equal to 1. And all of the other examples being further away than these three will have functional margin that are strictly greater than 1. Okay? And the examples with functional margin equal to 1 will usually correspond to the ones where the corresponding Lagrange multiplier is also not equal to 0. Okay, and again, this may not hold true. It may be the case that gi and alpha I equal to 0, but usually when gi is 0, alpha I will be non-zero. And so the examples with functional margin equal to 1 will be the ones where alpha I is not equal to 0. Okay. One useful property of this is that, as suggested by this picture and sort of true in general as well, it turns out that when you find a solution to the SVM optimization problem, you find that relatively few training examples have functional margin equal to 1. In this picture I've drawn, there are 3 examples with functional margin equal to 1. There are just 3 examples with this minimum possible distance to your separating hyperplane. And these are these examples with functional margin equal to 1. They are what we're going to call the support vectors. Okay, and this leads to the name support vector machine. There will be these 3 points with functional margin 1 that we call the support vectors. And the fact that there are relatively few support vectors also means that usually most of the alpha i's are equal to 0, right? So this alpha I will be equal to 0. For examples that are not support vectors. Okay. Let's go ahead and work out the actual optimization problem. So we had a maximum margin optimization problem. So let me go and write down the Lagrangian. And because we only have inequality constraints, right? We only have sort of GI style of constraints, no HI style of constraints. We only have inequality constraints, no equality constraints. I'll only have Lagrange multipliers of type alpha, no betas in my generalized Lagrangian. But my Lagrangian will be 1/2 W squared minus oops. Okay, that's my Lagrangian. And so let's work out what the dual problem is. Right? And to do that, I need to figure out what theta d of alpha, again, there are no betas here. So what theta d of alpha is min with respect to W and B of L B alpha. Okay, so the dual problem is to maximize theta d as a function of alpha. So let's work out what theta d is, and then that'll give us our dual problem. So to work out what this is, well, what do we need to do, right? We need to take Lagrangian and minimize it as a function of W and B. So, I mean, what is this? How do you minimize the Lagrangian? So in order to minimize the Lagrangian as a function of W and B, we do the usual thing, right? We take the derivatives of the Lagrangian with respect to W and B, and we set that to 0. That's how we minimize the Lagrangian with respect to W and B. So take the derivative with respect to W of the Lagrangian. And I'll just write down the answer. You know how to do calculus like this. Right, so I want to minimize this as a function of W, so I take the derivative and set to 0, and I get that. And so this implies that W must be that, okay? And so W, therefore, is actually a linear combination of your input feature vectors xi, right? This is a sum of, various weights given by the alpha i's and then times the xi's, which are your examples in your training set. And this will be useful later. The other equation we have is, partial derivative of Lagrangian with respect to B is equal to minus sum of I equals 1 to M alpha I. And so I'll also set that to equal to 0. Okay, and so these are my two constraints. And so if I move to the next one. So what I'm going to do is I'm actually going to take these two constraints and I'm going to take what I've worked out to be the value for W, and let's draw over this. I'm going to take what I've worked out to be the value for W, and I'll plug it back in there, right, to figure out what the Lagrange really is when I minimize this with respect to W. And I'll deal with B in a second. So, let's see. So my Lagrangian is 1/2 W transpose W minus right. So this first term, W transpose W, this becomes sum from I equals 1 to m, alpha I, yi, xi, transpose. Right. This is just plugging in the value for W that I worked out previously. Since this is W transpose W. And so when I expand out this quadratic function and when I plug in W over there as well, I find that I have that where I'm using these angle brackets to denote inner product. So, this thing here, it just means the inner product, xi transpose xj. Right. And the first and second terms are actually the same except for the minus 1/2. And so this simplifies to be equal to that. Okay. So let me go ahead and call this W of alpha. My dual problem is therefore the following. I want to maximize W of alpha, which is that big expression I wrote out. Oh, and I realize notation is somewhat unfortunate. I'm using capital W of alpha to denote that formula I wrote down earlier, and then we also had our lowercase w, the original parameter is the primal problem, right? Lowercase w transpose xi. So uppercase and lowercase w are totally different things. So unfortunately, the notation is standard as well, as far as I know. So, so our dual problem is that subject to the alpha rise must be greater than 0, and we also have that sum of yi alpha I is equal to 0. Okay. That last constraint was the constraint I got from this. Okay. That sum of yi alpha I was equal to 0. That's where that final constraint came from. Okay. Yeah. Let me just. I think in previous years that I taught this where does this constraint comes from is slightly confusing. So let me just take 2 minutes to say what the real interpretation of that is, and if you don't understand it, it's not a big deal, I guess. So when we took the partial derivative of the Lagrangian with respect to b, we ended up with this constraint that sum of yi alpha I must be equal to 0. The interpretation of that, it turns out, is that if sum of yi alpha I is not equal to 0, then theta d of w b is actually, excuse me. Then theta d of alpha is equal to minus infinity. We're minimizing, right? Yeah, right. Okay. So in other words, it turns out my Lagrangian is actually a linear function of my parameters b. And so the interpretation of that constraint that worked out previously was that if supervised yi alpha I is not equal to 0, then theta d of alpha is equal to minus infinity. And so if your goal is to maximize as a function of alpha theta d of alpha, then you better choose values of alpha for which supervised yi alpha I is equal to 0. Okay? And then when supervised yi alpha I is equal to 0, then theta d of alpha is equal to w of alpha. Okay? And so that's why we end up deciding to maximize w of alpha subject to that supervised y alpha is equal to 0. Right? Yeah, unfortunately, the fact we had to deal with b sort of adds just a little bit of extra notation in our derivation of the dual. But by the way, and so you know, right, all the action in the optimization problem is with w, because b is just one parameter, right? So, okay, let's check. Other questions about this? Okay, cool. So, we've derived the dual optimization problem, and really don't worry about this if you're not quite sure where this was. Just think of this as we worked out that this constraint, we worked out when we took the partial derivative with respect to b, that this constraint has the holds, and so I just copy that over here. Okay. But so we've now worked out the dual of the optimization problem. So our approach to deriving an optimal margin classifier or support vector machine will be that we'll solve this dual optimization problem for the parameters alpha star. And then if you want, you can then, this is the equation that we worked out on the previous one, right? We said that w, let's write this as alpha, w must be equal to that. And so once you solve for alpha, you can then go back and quickly derive, w, the parameters your primal problem. We worked this out earlier, right? And moreover, once you solve alpha and w, you can then plug this back into your. Once you solve for alpha and w, it's really easy to solve for b. Sort of b just as an interpretation of you have a training set. Right, you found the direction for w, so you know where your separating hyperplane's direction is. You know it's got to be, one of these planes. Right, you know the orientation for separating hyperplane. You just have to decide where to place this hyperplane. And that's what solving b is. So once you solve alpha and w, it's really easy to solve b. You can plug alpha and w back into the primal optimization problem, and solve for b. And I'll just write it down for the sake of completeness, but okay, and the intuition behind this formula is just that, find the find the worst positive example and the worst negative example, like let's say, this one and this one, say, and then you split the difference between them, and that tells you where you should set the threshold for where to place the separating hyperplane. And then this is the optimal margin classifier, or this is also called the support vector machine, if you do not use one more idea, which is called kernels. And I'll say a few words about that. But I hope the process is clear, right? So it's a dual problem. We're going to solve the dual problem for the alpha rise. That gives us W, and that gives us B. So there's just one more thing I want to point out as a lead-in to the next lecture, which is that, well, I'll just write this out again, I guess. Which is that it turns out we can take the entire algorithm and we can express the entire algorithm in terms of inner products. And here's what I mean by that. So I said that the parameters W is a sum of your input examples. And so when you need to make a prediction, right, someone gives you a new value of X, you want to evaluate the hypothesis on the value of X. That's given by G of W transpose X plus B, where G was this threshold function that outputs -1 or +1. And so you need to compute W transpose X plus B. And that is equal to alpha I yi. Okay. And that can be expressed as a sum of these inner products between your training examples and this new value of X you're trying to evaluate the algorithm on. Right? And this will lead into our next lecture, which is the idea of kernels. And it turns out that in the sorts of feature spaces we use to support vector machines, it turns out that sometimes your training examples may be very high dimensional. It may even be the case that the features you want to use are, infinite dimensional feature vectors. But despite this, it'll turn out that there'll be an implicit representation that you can use that will allow you to compute inner products like these efficiently. And this holds true only for certain feature spaces. It doesn't hold true for arbitrary sets of features. But when we talk about the idea of kernels in the next lecture, we'll see examples where even though you have extremely high dimensional feature vectors, you can compute, you may never want to represent xi explicitly, right? If xi is an infinite dimensional feature vector, you can't even store it in computer memory. But you will nonetheless be able to compute inner products between different input feature vectors very efficiently. And so you can, for example, you can make predictions by making use of these inner products. Right? I mean, this is just xi, transpose, right? You will compute these inner products very efficiently and therefore make predictions. And let's point out also, the other reason we derived the dual was because on this board, right, when we worked out what W of alpha is, W of alpha actually has the same property, that W of alpha is again written in terms of these inner products, right? And so if you actually look at the dual optimization problem and step for all the steps of the algorithm, you'd find that you can actually do everything you want. Learn the parameters alpha. Suppose you do optimization problem, learn the parameters alpha. You can do everything you want without ever needing to represent xi directly. And all you need to do is compute inner products between feature vectors like these. Okay. Well, one last property of this algorithm that's kind of nice is that I said previously that the alpha i's are zero only for the are non-zero only for the support vectors, right? Only for the vectors for functional margin 1. And in practice, there'll be usually fairly few of them. And so what this means is that if you're representing W this way, then W will be represented as a fairly small fraction of your training examples because most of the alpha i's will be 0. And so when you're summing up the sum, you need to compute inner products only of the support vectors, which is usually a reasonably small fraction of your training set. So that's another nice property because most of the alpha-rise was 0. Okay, and well, much of this will make much more sense when we talk about kernels. Let's quick questions before I close. Yeah.
I mean, it seems that for anything we've done to work, the point cloud has to be really well behaved. In that, if any of the points are on the kind of wrong side.
Yeah. No. Oh, yeah. You're right. So, for today's lecture, I assume that the data is linearly separable. That you can actually get perfect training error. I'll fix this in the next lecture as well. I'll relax that assumption. Yes.
So here we assume that we have 2 point clouds. Okay. So if you have multiple.
Oh yeah. So it turns out there are ways to generalize this to multiple classes, but I probably won't talk. But yeah, that's generalization. I'll leave for later. Okay, let's close for today then. We'll talk about kernels in the next lecture.